Okay, so we are very happy to hear Kevin Destagnol from Université Paris-Saclay, and he's going to speak on the Loughran Smeets conjecture for certain Châtelet type varieties. Please, Kevin.
Thank you. Thank you, Ramon. Thanks a lot for the invitation. It's a pleasure to give a talk here. So I will indeed talk about the Loughran Smeets conjecture for certain Châtelet type varieties. So I will spend a lot of time in explaining what is the Loughran Smeets conjecture and then what is a Châtelet type varieties. So I should mention before starting that all that I will talk about is joint work with Efthymios Sofos from Glasgow. So what will be our main motivation? A fundamental problem in algebraic geometry is to determine whether or not an algebraic variety or a given polynomial has a solution over the rational or the integers. This is, of course, a very difficult question, and it's kind of hopeless to answer this question in full generality. So when we have such an issue in analytic number theory, a very natural thing to do is to try to see if we can say something on average. So that's basically a polynomial with integer coefficients. And we will, in n variable, we will assume it to be homogeneous so that we have some projective algebraic varieties, and we will take it random. We will randomly choose a polynomial among some family. So for example, you can think of it as randomly choosing a conic in the plane. And the question we want to ask is, what is the probability that this randomly chosen polynomial has a solution over Q, of course, outside the trivial solution 0, 0, 0, which is always a solution because I chose my polynomial to be homogeneous. So we take a random polynomial and we want to know what is the probability that it has a non-trivial rational solution. So in other words, to ask the same question in the algebraic geometry setting, we will choose the family of algebraic varieties defined over Q. And in the remaining of the talk, Q will be given as the fibers, it is X and Y. So we will be given such a morphism and we will look at the fibers. And this will be our family of algebraic varieties. And the question will be, what is the probability that a fiber randomly chosen has a rational point? So we have actually several natural questions. The first question is there at least one fiber which admits a rational point? If there is such a fiber, is the set of fibers having a rational point finite or infinite? And since we want to use analytic number theory, I will be mostly interested in this case where we have infinitely many fibers. And then we can ask, is the set of fibers having a rational point Zariski dense? Or what can be said quantitatively? Can we say something quantitatively about this infinite set of fibers that admit a rational point? So this will be our main goal throughout this talk. Let me introduce a little bit further a few tools that we will need to actually answer this question. What can be said quantitatively? So we will be given X, an algebraic variety defined over Q, and I will take it to live inside Pn minus 1. The first thing we will need is the notion of height function, which will be of use to measure the complexity of the size of a point living in Pn minus 1. So I will take X to be a rational point on X. So since X is in Pn minus 1, I can represent X as this n tuple, x1, xn. And I can choose the xi's to be coprime integers. There are actually exactly two representatives such that the xi's are coprime integers. Then I will define the height of X to be h of X to be the maximum of the absolute values of the xi when I varies from 1 to n with coprime integers. This quantity h of X will be our notion of size and complexity of the rational point X. All right, so now the goal is to study the following thing. We will be given a dominant morphism pi from an algebraic variety X to another algebraic variety Y. And what we will want to do, we will want to study the following quantity that I will denote with a little bit heavy notation, n YH by B. So it depends on the variety Y, which is the base of our morphism. It depends on our morphism pi, on the height function, and on some real number B. What is this quantity? This is just the number of X. So, sorry, there is a typo here. This is Y. So we take X in Y of Q. So we take rational points on the base. This is a condition to ensure that we count only finitely many points. And then we will only want to count points, rational points on the base, such that the fiber above X has a rational point. So this is this quantity NYHB pi. This is the number of rational points on the base of height bounded by B, such that the fiber has a rational point. And the goal of the talk will be to try to understand the asymptotic behavior as B goes to infinity of this quantity NYH pi B. So let me first make a little remark. The remark is the following. If you take a dominant morphism such that all the fibers have a rational point, then this condition, which is precisely to say that the fiber has a rational point, becomes always satisfied. And hence you're left with counting points X in Y of Q of height bounded by B. And in other words, we retrieve Manin's conjecture for the variety Y. And for this kind of counting problem, when we want to count rational points of bounded height, we have a famous conjecture formulated by Manin and some of his collaborators, we predict that this quantity should behave when B goes to infinity as some one where rho is just the rank of the Picard group of Y. I also should mention that the constant here that I denoted by C pair, sorry, there is a question right in the chat. I thought, yes, so to answer the question of Igor, is asking about the dependency on H. Oh, sorry. The dependency on H, yeah, here I fixed the height to simplify the notation, but we could choose any height actually on X. I don't know if it does answer the question, but I could actually ask the same question with a different height.
Okay. Yes, I understand.
Here I just fixed this to simplify things.
Okay, thanks.
Yeah, thanks for the question. So yeah, I was saying that the constant C pair received an interpretation by Emmanuel Pair in terms of geometric invariance of the variety Y. So we have a prediction, a full prediction of these constants, depending on the geometry and the arithmetic of the variety, a prediction for the power of B, and a prediction for the power of log B. So here we will seek a similar asymptotic formula in the case of our new problem, where we want to count point of bounded height on the base such that the fiber has a rational point. So let me first start with two fundamental examples that will show up later in the talk. So the first example is the family of variety given by this, which is basically circles in the plane of radius square root of R. And we want to count the R smaller than B such that this circle in the plane has a Q solution. The solution being in X and Y. So this is quite elementary. It was proven by Landau that this quantity behaves when B goes to infinity like a constant times B divided by log B to the 1/2. So the first thing that we can see is that we have a similar shape for the asymptotic formula. We have a power of B and we have a power of log B. The difference being that the power of log B in Manin's conjecture, it was an integer. Here it can be a negative rational number. But we still see a similar asymptotic formula. We also have an explicit formula for the constant C0, which is 1/√2, and then we have this nice Euler product. So the product is only over primes congruent to 3 mod 4 for one reason, is that the only primes for which you can have an obstruction for this equation to have a solution are the primes congruent to 3 mod 4. Then you need the p-adic valuation of R to be even. This explains also why we have a p² here. So we have a nice expression of the constant which is an Euler product. This is also very reminiscent of what happens in the setting of Manin's conjecture and with the constant predicted by pair. All right, so maybe a word on how one can prove this thing. You can use it, you can prove it using the associated Dedekind, the Dirichlet series, sorry, and using Zellberg-Delange, or you can use some sieve methods. The second fundamental example that I would like to discuss is due to Serre and goes back to 1990. And it was actually improved very recently by Efthymios Sofos and Nick Rome just this year. So the problem is the following. We will look at planar diagonal conics in P3. Yeah, sorry, is there a question? No, okay, so we're looking at planar diagonal conics of equation a1 x1 squared plus a2 x2 squared plus a3 x3 squared. And we want to count the probability that such a planar diagonal conic has a rational solution. So namely, we want to count when the number of AI bounded by B such that this equation has a solution in x1, x2, x3 rational. And what Serre actually proved using the large sieve and also quite a lot of algebraic geometry is that this quantity can be upper bounded by b cubed divided by log b to the 3/2. So once again, we see an asymptotic formula of a similar shape, some power of b times a power of log b with some negative rational number. So what can be said here using this is that already the probability for a planar diagonal conic to actually be, because here, if you divide by the number, the total number of choice for AI, which is b cubed, you get an upper bound of 1 over log b to the 3/2, and that goes to 0 when b goes to infinity. So the probability for a random diagonal conic to have a solution is actually 0. And the question Serre asked in his paper in 1990 was, is this upper bound actually sharp? A few years after Serre, two people independently, Houli and Guo, actually proved lower bounds for the same counting problem of the same order of magnitude. And only recently, so in 2022, Sofos and Rome actually managed to promote this upper bound and this lower bound into an asymptotic formula. And what they proved is that this counting problem is actually equivalent to some constant times b cubed over log b to the 3/2. All right, so we've seen two fundamental examples of counting problems. And I'd like now to move on to the formulation of the conjecture of Loughran and Smeets. So their work actually originated from the paper of Serre in 1990. They tried to understand if this bound was sharp or not, and they tried to generalize the result due to Serre. So what they did is that they considered dominant morphism pi from some algebraic variety x to Pn-1. So they chose as a base projective spaces. I don't want to actually describe those assumptions here, but they're quite mild assumptions on this morphism. And what they showed is that the number of fibers of bounded height that have irrational points can be upper bounded by b to the n divided by some power of log b, where this power of log b is, I will denote it by delta pi. I will come back to this power of log b a little bit later in the talk. So actually, they generalized the result of Serre to a large class of morphism. How did they prove such a thing? They actually upper bounded this by something which is a little bit easier to handle. Counting rational points is actually something difficult, and usually counting points over local fields is something which is a little bit easier. So what they did is that they upper bounded the number of fibers having a rational point by this quantity n log, which is basically the number of points on the base of bounded height, such that the fiber is not rational, has a rational solution, but has a solution everywhere locally. So they counting the fiber of bounded height such that the fiber has a rational over QP for all primes P and over the reals. And this is much easier to handle. And this is actually this quantity that they managed to upper bound by b to the n divided by log b to some constants. And their proof actually relies on the same tools as the one by Serre, namely the large sieve and some algebraic geometry and the long veil estimates. All right, and what one can notice is that the two examples that I showed you, the circles in the plane and the conics, they actually satisfy the Hasse principle. And so having a rational solution or being everywhere locally soluble is actually the same problem. And that's why, this explains why in those cases, people were able to actually find asymptotic formula for this quantity. All right, so what actually Loughran and Smeets did in their paper to get this upper bound led them to make a precise conjecture regarding the quantity n log. They actually conjectured that this quantity n log, which is the number of points in the base of bounded height such that the fiber is everywhere locally soluble, they conjectured that this should be equivalent to a constant times b to the n divided by this power of log b to the delta pi. And this actually agrees with the result I presented you in the case of the circles and in the case of the diagonal planar conics. So let me, before saying a little bit more on this delta pi, say a few words about what is known regarding these conjectures. Loughran and Smeets in their original paper, they proved this conjecture when this invariant delta pi is actually 0. Then a little bit later, Dan Loughran and Loughran with Takloupigash and Tanimoto, they proved the same conjecture for some morphism for which the variety X has an underlying group structure. In doing so, they were able to use tools coming from harmonic analysis to obtain such asymptotic formulas. And the last example was due to Sofos and Wisse-Martindale in 2017. I will come back to this example later because it is quite related to the one I want to talk about today. One thing I should mention here is that in their conjecture, they predict a power of b, they predict a power of log b, which actually depends on the geometry of the morphism. And what was missing for a long time was a prediction for the constant c. What we would have liked to have is a prediction for c in the similar spirit as the prediction from Emmanuel Père for the constant appearing in Manin's conjecture. So for a long time, people had some ideas on which factors should appear in C, but there were still some new factors that people couldn't explain for the constant C in this problem. And so that's why it was quite important to have new examples for which one can prove this asymptotic formula in order to better understand this constant C. So that was our motivation with Efthymios. And actually, our work, on top of the work of Efthymios and Nick Rome recently, allowed Dan Loughran, Efthymios, and Nick to actually give a full prediction for the shape of this constant C. So now we really have a prediction on the power of b, the power of log b, and the constant C in terms of the geometry of the morphism pi. So now what I would like to do is to try to say a little bit more on this exponent delta pi and try to convince you that this is the right order of magnitude. One should expect this b to the n divided by log b to the delta pi. All right, so we will take, as usual, our morphism pi from x to pn minus 1, and we will introduce the following quantity. So I will denote this sigma p when p is a prime number. It will just be the number of point x in pn minus 1 of fp, such that the fiber above x has no smooth fp point. What I do is I divide this by the whole number of points in pn minus 1 of fp. This might seem a little bit weird, but why do we introduce this? Because the quantity 1 minus sigma p is basically the probability that the fiber above x has a smooth fp point. And when you have a smooth fp point, what's nice is that using Hensel's lemma, you get a qp point. So basically, you should think of 1 minus sigma p as the probability such that the fiber has a QP point. All right. So once we have this, Loughran and Smeets, what they showed is that on average, this quantity sigma p behaves like some constant divided by p. And this is this constant that one can call a delta pi. And this is the exponent of the logarithm. So more precisely, what they proved is that when you sum the sigma p for all primes p less than b, and you divide by the sum of 1 over p over all primes p less than b, well, this ratio converges, and we can denote its limit by delta pi. So this actually takes a lot of work to show that this limit exists. And that's what Dan Loughran and Arne Smeets did in their original paper. So one could take that as a definition of delta pi. I should maybe mention that there is another definition of delta pi, which is of course equivalent, and it's more geometric. It depends on the singular fibers of the morphism pi. And this is usually more useful to actually compute in practice the value of delta pi. But here, this definition of delta pi will actually be very useful to see that the power of log is actually log to the delta pi. All right, so to resume here, we have this sigma p such that 1 minus sigma p is basically the probability that we have a QP point on the fiber. And what we need to remember is that sigma p behaves like delta pi over p on average. Now, let's go back to our initial problem. So what we want to count is points smaller than b, such that the fiber has a solution everywhere locally. So we want the fiber to have a solution over QP for all primes p. So this quantity can be approached by the number of points of bounded height, and then I multiply by this quantity, which accounts for the QP solubility. Remember that 1 minus sigma p is basically the probability that the fiber has a QP point. So this is a good approximation of our counting problem. But now, using Loughran and Smeets, this sigma p behaves like delta pi over p on average. So I could replace this product by the product of 1 minus delta pi over p. And the number of points on Pn minus 1 of bounded height, it can be shown that this behaves like a constant and b to the n. So overall, our counting problem roughly behaves like b to the n times this times this product. Now, using classical results in analytic number theory, we know that this product should behave like 1 over log b to the delta pi. And so that's why we expect heuristically to have as order of magnitude b to the n divided by log b to the delta pi. So that's the conjecture of Loughran and Smeets. And so our main goal with Efthymios Sofos was to provide new examples for which we can prove this conjecture to actually better understand the constants. So are there any questions so far? All right, so if not, I'll move on to our result with Efthymios Sofos. So I will first introduce the family of varieties we will consider. So the problem we want to study will be the following. We take d to be a square-free integer, and we take the norm of the extension q of square root of d, so x squared minus dy squared. And we want that to be equal to a product of a bunch of polynomials times d squared. So basically, we're taking, again, a conic in the plane. We're fixing two coefficients, one being 1, the other one being some square-free integer. And the last coefficient, we will impose that it's a product of a bunch of polynomials. And we want to count the t such that this equation has a solution over the rational in x, y, and z. All right, so I should say a little bit more what are these fi. So these fi will be polynomials with integer coefficients and variables, homogeneous and irreducible. For technical reasons, we will assume that they all have the same degree. This can probably be removed, but yeah, this makes the technicalities much simpler in the proof. So we assume that they all have the same degree, and we have to assume that the total degree of the product is even. So this is to simplify the geometry of the morphism, and so that the problem is well defined. All right. So we have one more assumption, which, spoiler alert, will actually tell you that we will use at some point the circle method. We will assume that the polynomials f1, fr are actually a Birch system. So maybe there is no point in actually going through the precise definition, but basically what we have to remember is that we have to impose enough variables with respect to the degree so that we can apply the circle method. So this is a condition to ensure that the polynomials behave in a way randomly enough, and to ensure that the values taken by these polynomials are not too sparse. All right, so basically we want to study this equation, x squared minus dy squared is equal to a bunch of polynomials times z squared. And we assume the polynomials to have enough variables so that we can apply the circle method. All right, we are then interested in estimating the following counting function. We want to count the point in Pn minus 1 of Q of bounded height such that this has a rational solution in X, Y, and Z. So the theorem we proved with Efthymios Sofos is the following. We proved that this quantity n of b is actually equivalent to some constant times b to the n divided by log b to the r over 2. So this b to the n actually agrees with the prediction from the Loughran Smeets conjecture. Then we have this power of log b to the denominator. It can be shown that the constant delta pi here is equal to r over 2. So this is consistent with the conjecture of Loughran Smeets. And this constant, actually, some interesting phenomena appeared in this constant, but with the new formulation of the conjecture, this now agrees with the prediction for the constant c due to Loughran, Rome, and Sofos. All right, so why did we choose such an equation? Maybe I should say a word about that. We chose such an equation because if you take polynomials here with only one variable, basically what you get is what we call a Châtelet surface. And Châtelet surfaces are quite interesting surfaces from the arithmetical point of view. They are one of the first examples that we had of surfaces for which both the Hasse principle and the weak approximation failed. And in the setting of Manin's conjecture, those surfaces were quite interesting because they made some interesting phenomena appeared in the constant, which sometimes was not only like an Euler product, but was a finite sum of Euler products. So we thought that generalizing these Châtelet surfaces might actually give good insights regarding the constant in the Serre in the Loughran Smeets problem. And actually, it is indeed what happened. I will say a word at the end regarding what's interesting in this constant. All right, so let me now spend the rest of my time trying to explain a little bit the ideas behind the proof of this counting problem. So to simplify the exposition, I will take in the following d is equal to -1, and I will just take a product of two polynomials, which is the minimal case to see something interesting happening. If I take only one polynomial here, I don't see the interesting phenomena I was just talking about in the constant. So basically what we want to do is the product of two polynomials is equal to a sum of two squares. All right, so our first tool will be what we call perceiving. So this is making use of the following proposition, which is actually a very nice proposition. So we have to introduce a little bit of notation. So I will denote by C the maximum of the absolute values of my polynomials when t is between -1 and 1. Then let A be an arbitrary set inside Z2. So I take any set in Z2. And then here, what do I have? I have the number of t in z to the n, so integer vectors lying in between minus b and b, such that when I form the vector f1 of t, f2 of t, I lie in my set A, and I divide by b to the n. So basically here what I have is the probability that the vector f1t, f2t falls in A. And what we showed is that this probability is actually upper bounded by the natural density of the set A, which is the number of points in A between minus b to the d and b to the d divided by b to the 2d, where d here is the degree of the polynomial. So to reformulate, the probability that the vector f1t, f2t falls in A is actually upper bounded by the natural density of the set A. And the implied constant here is actually independent of B and of the set A, which is quite surprising. It depends only of the coefficient of the FIs. So maybe I should say a word on why this result is a bit surprising and only hold. Also, there is a question. T.
Kevin, it's a bit, again me. I guess the first line, the first display contains a typo, right?
Yes, you're
it
right.
Should be n, right?
Yeah, you're
in
totally right.
Dimensional case.
And in the number of variables, yeah, exactly.
Yeah,
sorry.
Okay.
So here it's an n. Yeah, you're right. So why is this result surprising and can only be achieved here using the fact that we have Birch polynomials? It's because imagine that I take n is equal to 1. So I take polynomials in one variable. And then here I just take one polynomial. So one polynomial in one variable. Then I take the set A to be the values assumed by my polynomial f. Then, of course, this left-hand side becomes 1, because it's always true that f of x lies in A. And this will tell you that the density of the values taken by f is positive in Z. And we know that this is only the case when the polynomial is of degree 1. So this is something which is very restrictive. To hope, this statement, to hope for such a statement in complete generality is actually completely hopeless. But in the case of Birch systems, so the condition on the number of variables being big enough implies that the values taken by f are not so sparse and the polynomials are independent enough so that we can hope for such an upper bound. I should mention that we don't necessarily have that the left-hand side is of order the right-hand side. Sometimes the right-hand side can be 0, and sometimes you can get an asymptotic. So it really depends, but we always have an upper bound. So how will we use this result? We will take a set of density 0. And hence, you will get here something that goes to 0 on the right-hand side. And this will tell you that up to a small error, there is probability 0 that the vector f1t, f2t actually falls in A. And this will be actually very useful to get rid of a lot of conditions, as I will explain in a moment. All right, so this is our major preceding lemma that we're using. So I maybe, okay, since it's already 40, I might skip the proof. So the proof actually is just using Birch results in his paper, forms in many variables, when he proves Hasse principle for hypersurfaces with enough variables. We just have to inject his result, and in 2 lines, the result can be obtained. So it's actually a surprisingly easy proof for a very nice result. So how will we use this proposition, this preceding lemma? So we will fix a quantity z, which will depend on b, and when b goes to infinity, we will need that z goes slowly to infinity. So this will be to ensure that we can use some Ziegel-Wallfisch type theorem at some point. What we will do is that we can assume using this proposition that when p is bigger than this bound z of b, p squared does not divide the product f1, f2. Indeed, how can we bound the error when p squared divides f1, f2? Well, we can use this lemma. taking the set A to be the set of integer n1, n2, such that either p squared divides n1 or n2, or p divides n1 and n2. This set has density 1 over p squared. So that's why we have 1 over p squared here. This bn here comes from this bn here. And so this is an upper bound for the number of t such that f1, f2 is divisible by p squared. Then we just have to sum over all the primes p bigger than z to obtain this. And this is the tail of a convergence series. So we get a little o of b to the end. And actually, we indeed get a correct error term. So we can assume up to an acceptable error term that p squared does not divide f1, f2. So here I'm cheating a little bit because what I would like to have here, if you remember, the main term we get is b to the n divided by some power of log. So here I would like to have a little o of the same thing. But actually, the set A we'll have to consider is not exactly this one. This is exactly this set, but with the condition n1, n2, the product of n1 by n2 is a sum of two squares. And when you use the density of this set, you will get 1 over p squared times some power of log. And you will get in the end a little o of b to the n divided by some power of log. So using this result, we can get rid of square factors for the product f1, f2, provided that p is bigger than some bound z. So we actually hope that this proposition could be used in other settings because, for example, you could get rid of big prime common factors. We could also do a similar reasoning to ensure that there is no prime p bigger than z, such that p divides f1 and f2. And so this is something that might have further application than just a counting problem I'm talking about. All right, so using the enough, p squared does not divide f1, f2. So now we can go back to our counting problem. So we fix this z, which goes slowly towards infinity. And we will at some point have a congruence condition modulo this w, where w is a product over all primes p smaller than z. So you don't really need to know what is this power. What's important is that w is a product of powers of primes p, where p is smaller than z. At some point, we will have congruence condition modulo w, and we will need this w to be smaller than some power of log. So that's why I need this z to go slowly towards infinity. All right, so now what we wanted to count basically was the number of t smaller than b, such that f1, f2 is a sum of two squares. Well, using the preceding lemma I just talked about, this can be approached up to a reasonable error term by the number of t smaller than b, such that f1 and f2 is a sum of two squares, but I can add the following condition such that when p is bigger than z and congruent to 3 mod 4, p squared does not divide the product f1, f2. But now, if f1, f2 is a sum of two squares, this means that the p-adic valuation when p is 3 mod 4 has to be even. So when p is bigger than z and 3 mod 4, the p-adic valuation has to be even, but it cannot be bigger than 2. So it has to be 0. In other words, we can replace this condition by counting the number of t smaller than b, such that when p is bigger than z and congruent to 3 mod 4, p does not divide f1 or f2. And for the rest, we have, of course, the condition that the valuation must be equal. And we have the condition for the real place. So what's interesting here is that we actually got rid of infinitely many obstructions for the product f1, f2 to be a sum of two squares. All the obstructions when p is bigger than z. For those obstructions, they're easy to deal with. It's just that p shouldn't divide fi of t. And we're left with only finitely many obstructions, which will be easier to deal with. So that's the strength of this preceding step, allowing us to deal with infinitely many obstructions at once. All right, so now what we will do once we have this is we will freeze the value of f1 of t and f2 of t. So I will call N1 F1 of t and N2 F2 of t. Doing so, I get that this N1 and N2 are smaller than b to the d. When p is bigger than z and congruent to 3 mod 4, p shouldn't divide ni. And when p is smaller than z, we have the condition ensuring that N1, N2 is the sum of two squares. And then what we want to count is the number of t smaller than b, such that fi of t is equal to ni. So here I did nothing complicated. I just froze the values of fi of t, setting them to be equal to ni. And here what's interesting is that the inner sum here, the number of t such that fi of t is equal to ni, is precisely the problem that Birch was tackling in his paper Forms in Many Variables. So what we can do is we can just re-inject the result coming from Birch to estimate the inner sum. So using a truncated version of Birch, one can give a good estimate, a good asymptotic formula for this inner sum. So you get some power of b, you get some Archimedean density, and then you get this density modulo w. So one of the strengths, again, of the preceding is that we don't need to implement, again, the circle method. We were just able to re-inject the circle method from Birch without having to work it over again. So now what one can notice is that this quantity here, this density modulo w, only depends on the ni modulo w. It only depends on the congruence classes of ni modulo w. So we will do something very natural, which is to split the ni in congruence classes. In doing so, basically, so I'm skipping a few technical steps, we end up with the following sum. So we have a sum modulo w replaced by mi, and we have a congruence condition on top of that. So we will be interested in the inner sum now. We want to count m up to some bound, such that when p is bigger than z and 3 mod 4, p does not divide mi. So this is not a problem. This is easy to deal with. And then we still have this condition, this obstruction for m1, m2 being a sum of two squares when the primes p are smaller than z. When p is smaller than z and 3 mod 4, we need to require that m1 and m2 have the p-adic valuation of the same parity, and we have to require that m1, m2 is positive. All right, so how do we deal with this finitely many obstruction? Actually, when m1, m2 is a sum of two squares, m1 and m2 are not far from being each a sum of two squares. And actually, this is what we're trying to implement here. We're going to try to split this sum into a sum involving m1 or something related to m1 being a sum of two squares, and a sum involving m2 or something related to m2 being a sum of two squares. So this will be our goal now, to try to split this sum using the fact that we only have finitely many obstruction left. So how do we do that? Well, we have to introduce this integer mu, which is the product of p, where p is smaller than z and congruent to 3 mod 4. And we impose the condition that the p-adic valuation of mi has to be 1 modulo 2. Basically, I just take the product of all primes p, which can cause an obstruction, which means they are smaller than z and they're congruent to 3 mod 4. And they can cause an obstruction for m1 to be a sum of two squares, because the valuation of mi is 1 mod 2. One thing I should mention is that here there is a subscript I, and here there is no subscript. So why is that? It's because the condition here ensures that the p-adic valuation of m1 is the same as the p-adic valuation of m2. So this mu does not depend on the choice of I. All right, and so what we do have now is that when you take this integer mu, mu divides m1 and mu divides m2. And m1 over mu and m2 over mu, up to a sign, they become sums of two squares. Because when p is bigger than z, you don't have any obstruction, because p does not divide mi. And when p is smaller than z, the valuation becomes even in each cases. So M1 and M2 are sum of two squares up to this integer mu and up to a sign. So then one can show that this defines, actually this mu defined a set of valuation. So basically you take all the prime p smaller than z and congruent to 3 mod 4, and you assign 1 or 0 according to whether or not your prime p appears in the mu here. So what we will do then is that we will take into account the sign and this integer mu, and what we have is that each of the mi up to this sign and up to this mu will become a sum of two squares. Doing so, we can split the previous sum here according to all the possible values of the sign and of this mu, which only gives you finitely many possibilities because I only have finitely many primes and obstructions left. So in doing so, I get a sum over all the signs, a sum over all the mu, and here I get my sum over t modulo w, and the sum I had for which m1, m2 was a sum of two squares now splits into two sums, the product of two sums, one involving m1 divided by s mu, which is a sum of two squared, and the second sum involving m2 divided by s mu, which is also a sum of two squares. So we managed to actually split our sum into a product of two sums, where each of the SI of B is related to a quantity like the number of integer up to some bound in a congruence class modulo W, such that M is a sum of two squares. And actually, you recognize up to these congruence classes, these congruence conditions, the first example I gave you at the beginning of this talk. Counting the number of integer up to a bound, so that this integer is a sum of two squared, which was my first example. One can deal with this extra congruence condition, provided that the modulus W is not bigger than some power of log B. And using this, one can actually prove asymptotic formulas for this quantity, which will be some function of W times b to the d divided by some square root of log. Putting all of this together here, one can actually prove the asymptotic formula that I mentioned at the beginning of the talk, which is the following in the case where we just have two polynomials. N of b is then becomes equal to some constant times b to the n divided by log b. And what I would like to mention about this constant is that all the terms are quite nice and easily interpreted, except for this omega. This omega becomes a limit when z goes to infinity of this contribution. And in terms of geometry, what we actually did is that we transferred the counting problem for on our original variety, f1, f2 is a sum of two squares, into a contribution on the following algebraic variety given by the equation fi of t is equal to something times a product of two squares. And this is what we call a torsor associated to the underlying variety. And so in other words, this omega can be interpreted as the contribution of each of these torsors. And this is the first time to our knowledge that we get a contribution in such an asymptotic formula coming from infinitely many torsors. Here, this limit here, in the end, provides infinitely many torsors. So we don't get an Euler product, like in the examples I gave, but we get somehow an infinite sum of Euler products, taking the limits, which was, to our knowledge, the first time something like that happened. All right, so maybe to conclude, I would like to resume a little bit what we did in our example. So we proved the Loughran Smeets conjecture in a new case, and in this case we made new factors appear in the constant, in particular regarding this infinite sum of Euler products. Probably one interesting thing to to take from this this result is this pre-sieving technique, which of course only works because we have BERT systems, but we really believe that this pre-sieving technique could have many more applications, even maybe in counting rational points of bounded height. And yes, we also have this sum of contribution of the torsors. And yeah, I think I'm gonna stop here. I'm a little bit early. Thank you.
Oh, it's perfect. Thank you. Well, thanks. Open for questions now. Go crazy.
May I ask?
Yeah, sure.
Kevin, what if you separate your variable t in different classes depending on the GCD of f1, f2? And then the whole thing will split into two equations, right?
Wait, what do you mean at the start?
I assume that all numbers are relatively prime, right? That
F1, F2. No, the variables or F1, F2?
Well, yes, I want to assume that f1 and f2 are relatively prime.
Yeah.
Then you have two equations instead of one, right? Two independent equations.
Yes.
But of course, you can just assume that the GCD is D, and then you adjust the equations to D. Can this help somehow? Kind of to split problems in the for f1 and for f2.
Yeah, maybe this could work. Let me think. I would need to. So you split, but no. Yeah. Yeah. I mean, we didn't try that, but maybe this could also work. I would need to try to write down the details, but I mean. Yeah, that's a good point, I guess.
And sorry, I have a very small technical question. When you estimate the number of values for which the polynomial is divisible by a prime square, I believe in this estimate, but it's not immediately straightforward because congruence
which
is
estimate?
primes.
Sorry, can you say again which estimate?
This bound at the very bottom, right?
Oh, this slide, yeah.
Yes, yeah. How do you put p squared in the denominator? It's not immediately straightforward, right? Because it's congruence modulo p squared. Yeah, in a ring, it's not a field anymore.
The density of A, the density of A is one over p squared.
The density of A, yes, but you count the number of values of t for which p squared divides f1
I fix
t
p first. I fix my prime p bigger than that.
Yes, yes.
And then I take this A, which has density 1 over p squared.
Okay. Okay. But
I mean, you could take two A's, like you could take a first A, which is.
I thought you need to count the number of values of t for which p squared divides f1t. And
yeah, but no, I get a bound for this number using my proposition.
Okay. So right, you pass
so
it.
I just need to count the integers.
Yeah.
So this has density 1 over p squared. So you get the 1 over p squared here and the bn from here.
Right. Okay.
And yes, the thing you're saying is bounded by bn over p squared, and then I solve over.
Okay, makes sense. Thank you. Thanks.
Thank you.
So, okay, I had a stupid question this time. So, you say that this proposition. So, is this proposition? Are you supposing something about this FIs? Birch?
Well, they are Birch polynomials, so they have many variables.
So, if you were to summarize in words what this Birch thing means, so many variables and.
Yeah, basically, like if you just take one polynomial, it means that the number of variable has to be bigger than 2 to the degree times the degree minus 1.
Okay.
So you need to have exponentially many variables in terms of degree. And so the real definition when you have several variables is the following here. So you get this d minus 1 times 2 to the degree. And you don't take here the number of variables, but you take the codimension of some affine variety given by the rank of the Jacobian.
Okay.
But yeah, roughly this means that you have enough variables.
I see. And even stupider question is, so in the yeah, like right here I can see that you're solving the equation with many polynomials, but your main proposition is for two polynomials. Is how it's like that's all you need, or
well, the thing works basically the same. I can assume that p squared does not divide the product using the same arguments, and then all the rest follows in exactly the same way. I'm left with finitely many obstructions, and I split the sum into a product of R sums.
okay.
So basically,
right.
yeah, everything works the same.
Okay. So you just chose two for the exposition.
Yeah, to simplify the
okay.
exposition.
All right.
But yeah, it would work for R and it would work for any D. We just need to have a nice way of knowing when x squared minus dy squared is solvable, is equal to an integer.
I see. Okay. I thought you were saying that everything like this boiled down to the case that you solved.
No, it's just that the method is the same.
Okay. Yeah, that makes understood better now.
Yeah.
That's cool.
We're actually wondering if we could replace the norm of a quadratic extension by a more general norm of any number field.
Okay. All right.
But yeah, so far
You start with the cube, right?
yeah, because in general, you don't have a nice way of knowing when an integer is the norm of, like here we just have nice congruence conditions.
Yeah, but like, okay. I don't know. No, I was reading I mean, I never read. Okay, maybe I would close. If nobody else has a question, I will close for questions and say the very exclusive thing I have to say after. Okay. All right. I'm gonna close the recording. Stop the recording.